I'm Claire Gilliam, and this is my lab on the motion of a falling object. So first, we have our introduction. What is this lab's purpose? Well, we want to observe the motion of a ball dropped from rest and then compare those observations with two computational models we create. We use Tracker to plot the object's vertical position and track it as it fell, and then GlowScript to create models of an object falling from rest with and without drag. We use Newton's second law, which states that the net force is equal to the change in momentum over the change in time, which can further be reduced to the velocity update formula. And then we also used the idea of the force of gravity near Earth's surfaces is equal to the mass of the ball falling times g, or 9.8 meters per second. And then we used the idea of the force of gravity, which is equal to -1 times the proportionality constant times velocity squared, moving or acting in the opposite direction of motion. And then we also use the position and velocity update formulas, which just were used in the computational models to update the ball's position and velocity as it fell. The results were the tennis ball did accelerate downwards. The model with drag is more accurate to our observations as it includes air resistance, same as the real world. And then the model with drag also allows us to see and interpret the object's terminal velocity. So, modeling the experiment, our assumptions are the ball is falling straight down, and there's no motion in other axes such as the x or z axis, and the ball's initial velocity is actually 0 meters per second. And then defining the system, we see that the tennis ball is the system and the surroundings is everything else. So, in our diagram, we see that the initial position, as it begins to fall, gravity is much bigger than drag. However, as time moves on, drag increases by the square of velocity. So, the experiment observations. First, we wanted to drop the tennis ball from rest, record the ball falling, and upload this video to track and plot the ball's y position on a position versus time plot. It looked like this. And as we can see, the ball's position. Next, we have our computational model. So first, we saw that the mass of the ball is 0.056 kilograms. The initial position is just at the origin, so 0, and the initial velocity is also 0. The tracker frames per second is 60 frames per second, so that's where we get 1 over 60, or 0.01 seconds. And then g is 9.8 meters per second. J hat, or the unit vector, is just 1 in the positive y direction. And for this, because we're not considering drag in this model, b is 0. There is no drag force. However, in the initial conditions for the model with drag, we see it's pretty much the same. However, b is equal to 0.008, which we approximated to be as close to real-world observations as possible, as this model does include drag. The final conditions are the same for both models. We see that t is equal to 0.667 seconds, because that's when the ball hit the ground. The net force is equal to the drag plus gravity force. However, for the model not including drag, we see the drag is 0, so the F net is just the force of gravity. The velocity of the ball is updated using the velocity update formula, and the position is updated using the position update formula. Finally, t moves forward by 0.017 seconds each time. And we get our vector arrows by multiplying the force times the arrow scale, which in this case is 0.5. Finally, we have our discussion and our conclusions. So first, our comparisons. From 0 to about 0.1, all the graphs generally look similar. However, they move away from each other. All three graphs move away from each other once t is around 0.2. Both models actually overestimate our observations and say that the ball would be further down than it actually was. However, the model including drag and our observations become very similar at around t is greater than 0.5, as the drag and observational models both include air resistance, which makes this relationship make sense. However, these discrepancies at around 0 to 0.5 show that there are probably errors in our simulation, such as not correctly choosing the ball's position and tracker, the drag coefficient obviously not being entirely accurate as we had to approximate it, the initial motion in there being initial motion in the x or z axes when we dropped it, or v not being 0 and possibly being released slightly up or down. Finally, we have our concluding questions. So what does this all mean? What models predicted terminal velocity? Well, the model without drag doesn't predict a terminal velocity, and only the model with drag does. As we see, the model with drag shows that the velocity is probably approaching around -5.7 or 8 meters per second. What if the ball was thrown down? Well, we can see this when we plug in -1 as the initial velocity in our model. When we do this, we see that this does affect the terminal velocity. The terminal velocity becomes lower than our velocity if the initial velocity was 0. We see that it actually starts to approach around -6.1 meters per second as we had an initial velocity downwards. All right, thank you.